Good afternoon, faculty and students. Today we are presenting our senior project on brazing work cell design and simulation. We are team number 4, section B, and I would like to present the rest of the team. Reef Off alum, Kara Coolin, Dustin Hodge, Bryant Vieira, and our project advisor is Dr. Elips Macion. Throughout our presentation, we will be discussing these topics. Before we begin, I would like to give some background information on the company Yinlin TDI Thermodynamics. They were first established in 1958 and currently have 4 locations in the United States. And they manufacture heat exchangers, oil coolers, filter modules, EGR modules, engine brake systems, and aluminum castings. We visited the location in Ontario for our senior project.
Project description. Yinlin gave us a project working on the design and development of an OEM Mustang heat exchanger for a Ford vehicle to be produced in 2024, shown in the picture to the right. They wanted us to design fixturing for torch brazing operations compatible with the equipment that they already own to save cost. They also wanted a fixture for go-no-go final inspection gauging, along with designing a work cell for increased labor efficiency through 5S. Project description continued. The project that we worked on is still in the planning stage and is expected to begin development in 2024. This did mean that parameters of project design would be flexible and could be changed at a later time, but having this limited information of what the company was planning also made it difficult at times. On the table above, we have a component breakdown of the cooler assembly that corresponds with the picture below. The parts of the assembly in gold are received pre-assembled, with the gray parts being involved in the on-site assembly. The expected annual production quantity for this assembly was given by the company to be 75,000 pieces per year. Project sequence. This was the timeline for our project sequence. Step 1, research facility layout and processes and machinery the company had available. Step 2, research different brazing methods. Step 3, design fixturing for brazing and go-no-go final inspection. Step 4, investigate ways to improve work cell for optimized 5S and improved labor efficiency. Yinlin facility. We visited their Ontario facility to investigate what equipment they had available, the layout of the work floor, the work cells that they had set up, and the distance between operations. Unfortunately, at the time of our arrival, the equipment was not set up to operate and was lacking in overall maintenance. But the company's plan was to refurbish it before production so that it would be operable for their process. Their brazing and go-no-go inspection fixtures did give us a direction to lead our design process for creating our own fixtures though. We planned to model the brazing workstation with our part designs that would allow us to see the clearances between the automated pathway of their equipment and the fixture position.
Continuing on with the project, we came across some issues on deciding what brazing method to use. The ones we considered were torch brazing, furnace brazing, and induction brazing. We compared and contrasted these 3 brazing methods. The heat source for torch brazing is oxy-fuel gas. However, it is difficult to control and requires skilled labor, and it is for continuous parts. However, it does come with a larger heat effective zone. The average cycle time is 30 seconds as compared to furnace brazing, where it requires no skilled labor and it is for batch parts or continuous parts, and it is heated uniformly. The average cycle time is 50 seconds. Lastly, for induction brazing, the heat source is AC current and requires no skilled labor and is for continuous parts, and it does come with a smaller heat effective zone. The average cycle time is 12 seconds. We then began to list the pros and cons of torch brazing and induction brazing. Some of the pros for torch brazing was equipment is already on site, employees already have experience with this method and equipment. However, some of the cons is slow production, and it comes with fumes and requires proper ventilation, and the equipment is 10 years old and it has a longer heating time with more exposure to oxidation. Some of the pros for induction brazing is faster speed of production, increased quality of joints repeatability, increased energy efficiency, and improved safety, and reduce downtime and increase reliability. Some of the cons is having to purchase the new equipment, having to establish new work instructions, and retrain the employees.
At this point in the project, the company did not have a finalized cooler design for their assembly, so they sent us 2 versions that they had up for consideration. We have an interactive video below using Fusion 360 to give you a 3D view of both versions of the cooler, as well as differences between them as the models are superimposed. The main differences being circular pipe extensions coming out from the front face of the core and the mounting plates that extrude out from the top view of the core as shown. We also have some overall part dimensions on the right between the two variations to help with visualizing the sizing of the parts being produced. Difficulties with torch brazing and fixture design. Shown to the right is their torch brazing machine that would cycle forward and back to apply even heating to create a bond between the assembly parts and the preforms. Our initial approach to the project was to provide what the company requested, a fixture design for the part that would be compatible with their current equipment. This posed some challenges, both in design and in creating a time-efficient cycle time that could be done with one worker. The reason was that the part geometry would require 2 brazing operations due to the different elevations of the brazing locations. We considered that we could design a fixture to have an adjustable height so that both brazings could be done with one setup. This would save some time. Although it sounded like a good idea, we decided to try a different approach instead by changing the brazing method to one that would allow us to perform the 2 brazing operations simultaneously.
When designing the fixturing, we wanted the setup to be quick, easy, and clean. One of the lean elements we used was a concept known as poka-yoke. Poka-yoke is a technique to error-proof a process. We would do this by ensuring that our parts must be in the proper locations for the braze to take place. To do this, we used a series of positioning blocks and clamps to hold the core, jumper tube, and fitting block together. Here's a video of how an operator might put the assembly together to braze. First, the operator will place the core on the base plate and slide it against the 2 positioning blocks and secure it in place with a blue clamp. Next, the operator would insert the preforms onto the jumper tube and slide it into place. Then, the operator would engage the top clamp and place the fitting block onto the rail. Here's a better view of the braze area. The jumper tube rests on a positioning die with a semicircle 10/1000 of an inch larger than the jumper tube's diameter and has fillet edges to ease the access. This forces the jumper tube to be concentric with its braze point on the core. Tube also rests back on another positioning block to align fitting block on top of it, which in turn is kept straight by the rails.
Our work cell design for induction brazing consists of 3 stations that are in close proximity to optimize travel time by the singular worker. Brazing, cooling, gauging, and torquing are all done at the same station. The work cell station for torch brazing accommodates 2 stations of brazing. The cooling and torque station are separated from the braze station, as well as the gauging station, which stands alone from other operation stations. The storage and part rack are located on the ends once again, providing convenient locations to pull parts as well as store finished products. And our work instructions are indicated on this flow process chart. As you can see, we start with the pallets received, and we work our way all the way through brazing, gauging operations, and then we end up shipping the product. Our process plan will accommodate the 75,000 unit annual demand. Daily production is set to produce 313 units a day. Our ordering schedule is on a weekly basis, and we will order 2,000 parts each week.
We use ProModel to simulate the 2 different processes. The model on the left shows their current proposed method, where Yinlun would torch braze the parts using 2 operators. They would unpack the parts, set them to braze the jumper tube to the core, and then move them to a second braze location to braze the fitting block onto the jumper tube. The model on the right shows our proposed setup using induction brazing. And as shown before, all the assembly operations occur in one location and with one operator. We went with induction brazing as it was the cleanest, fastest method. We simulated 60 replications to simulate 2 months worth of work to ensure a minimum number of boxes can be reliably made. For torch brazing, we had on average 11.87 boxes, which would make 593 parts per day and 2,965 parts per week. However, we only order in 2,000 parts per week, meaning we would be overproducing 437 parts. Our excess parts can be stored, and every 4 weeks, we will have enough extra parts made to skip a week of production. Torch brazing has an increase in productivity of about 28%. For induction brazing, we have on average 6.82 boxes per day, which is 1,700 parts per week, meeting our weekly takt time of 1,565 parts. This leaves 142 parts excess a week, which allows us to have enough excess parts made to skip our pallet order for the 12th week and an increase in productivity of about 9%. Although induction brazing has a lower increase in productivity, it meets the takt time while using fewer employees and reduces overproduction.
The economic analysis compared the two different brazing methods. Despite induction brazing requiring more equipment costs, it proves to be the most cost-effective due to its lower labor expenses. The annual manufacturing cost for induction brazing is just over $380,000. The majority of the cost comes from the preform material that has an annual cost of $340,000 to meet the current demand. The charts on the screen show the budget allocation for each brazing method. Induction brazing uses 9% of the budget for labor, while induction brazing uses 16%. As time progresses, induction brazing will continue to be a smart decision economically, as Torch's annual compounded costs increases at a faster rate. Our team would like to acknowledge the courses that helped us complete this project. The manufacturing and industrial engineering courses we have taken here at Cal Poly Pomona are listed on the screen for your reference. This concludes our presentation. Are there any questions?